A wormhole is fundamentally a topological feature, representing a shortcut connecting two distinct regions of spacetime, often visualized as a handle or tunnel. Mathematically, this structure requires a solution to the Einstein field equations that describes a throat connecting two asymptotically flat regions. The key topological distinction is that the spacetime manifold is not simply connected, meaning not every closed loop can be shrunk to a point. The simplest model, the Einstein-Rosen bridge, arises from extending the Schwarzschild metric, which describes the geometry outside a non-rotating, uncharged black hole. This extension reveals a connection between two separate universes, or two distant regions within the same universe. The geometry dictates that the throat of this bridge is dynamic, opening and closing rapidly. The Einstein-Rosen bridge is the maximal analytic extension of the Schwarzschild solution, mapping four distinct regions of spacetime. This structure is inherently non-static. The throat opens and closes too quickly for light or matter to traverse. The geometry is characterized by two event horizons, one for each universe, which act as one-way membranes. An observer entering the bridge from one side is guaranteed to hit the central singularity, never reaching the other asymptotic region. To fully map this structure and understand the causal relationships, Kruskal-Sakaris coordinates are necessary, transforming the singular coordinate system of Schwarzschild into a smooth manifold across the horizons. This initial model, while mathematically elegant, is therefore not a viable mechanism for interstellar travel.
The Schwarzschild wormhole is inherently non-traversable because the throat rapidly pinches off, collapsing to a singularity before any signal can pass through. The geometry dictates that the proper time required for an object to cross the throat is longer than the lifetime of the throat itself. This rapid collapse is a direct consequence of the matter content, or lack thereof, satisfying the standard energy conditions of general relativity. The event horizons ensure that anything entering from one side cannot exit into the other asymptotically flat region, making the bridge a transient connection rather than a stable pathway. This non-traversability means the original Einstein-Rosen bridge is purely a mathematical description of spacetime connectivity near a black hole singularity. To create a stable, traversable wormhole, the throat must be held open against the immense gravitational forces attempting to collapse it. This stabilization requires a violation of the Null Energy Condition, which states that for any null vector, the energy density measured by an observer moving along that path must be non-negative. Violating this condition means the stress-energy tensor must contain regions of negative energy density. This hypothetical substance is termed exotic matter. Exotic matter exerts negative pressure, effectively pushing spacetime outward, counteracting the inward pull of gravity at the throat. Without this negative energy density, any attempt to traverse the wormhole results in immediate gravitational collapse. The first fully analyzed model for a traversable wormhole was developed by Morris-Thorne in 1988. These solutions are static and spherically symmetric, specifically designed to allow two-way travel. The metric requires the exotic matter to be concentrated around the throat, maintaining a stable radius and preventing the formation of event horizons. Unlike the Schwarzschild solution, the Morris-Thorne geometry is geodesically complete, meaning objects can pass through without encountering a singularity. Crucially, while the exotic matter density must be negative locally at the throat, the total mass of the wormhole system can remain positive, satisfying certain global constraints. These models provide a framework for analyzing the physical requirements for stable interstellar shortcuts.
If a traversable wormhole mouth is manipulated, profound consequences for causality arise. By accelerating one mouth relative to the other, or placing it near a strong gravitational field, time dilation effects create a significant time difference between the two ends. This configuration transforms the wormhole into a time machine, specifically a closed Timelike curve, or CTC. An observer entering the advanced mouth and exiting the retarded mouth could potentially interact with their own past. The existence of CTCs violates the principle of causality, leading to paradoxes, where an event could prevent its own cause. This potential for time travel is the most challenging theoretical hurdle for traversable wormholes. The potential for causality violation led Stephen Hawking to propose the chronology protection conjecture. This conjecture posits that the laws of physics prevent the formation of closed time-like curves, thus forbidding macroscopic time travel. While not a proven theorem, it suggests that quantum effects might intervene to prevent the creation of a time machine. Specifically, quantum field theory predicts that vacuum polarization near the wormhole throat could generate sufficient positive energy density to destabilize the exotic matter required. This influx of positive energy would cause the wormhole to collapse before a CTC could be fully established, thereby protecting the integrity of chronological order in the universe. A profound connection between wormholes and quantum entanglement is suggested by the ER equals EPR conjecture proposed by Maldacena and Susskind. This hypothesis suggests that two maximally entangled particles, known as an Einstein-Podolsky-Rosen pair, are connected by a non-traversable wormhole, specifically an Einstein-Rosen bridge. This connection implies that the geometry of spacetime is fundamentally linked to the quantum information structure of the universe. If this conjecture holds, entanglement is not merely a correlation, but a physical connection through spacetime geometry. This framework attempts to bridge general relativity and quantum mechanics by suggesting that the connectivity of spacetime is equivalent to the quantum connectivity of matter.
From a topological perspective, wormholes introduce non-trivial connectivity into spacetime, changing its global structure from simply connected to multiply connected. This change fundamentally alters how paths and loops behave within the universe. While currently purely theoretical, the study of wormholes provides critical insights into quantum gravity and the limits of general relativity, particularly concerning energy conditions. Current research focuses on whether quantum field theory allows for localized violations of the energy conditions sufficient to sustain a microscopic transient wormhole. The possibility of microscopic wormholes, potentially stabilized by quantum effects, remains an active area of investigation, exploring the ultimate limits of spacetime topology.